So it's my pleasure to welcome Leonidas Lampropoulos, who's going to tell us about property-based testing in Coq.
Yep. Thanks. Yeah, when David sent me an email about a chance to speak at Lean, I was excited because we've been working on property-based testing in Coq for quite a while. So like testing before you prove something in a proof assistant. Yeah, I'm really excited about showing you what we've done there. And if anybody wants to do something similar or tell me what you would want from such a tool so that we collaborate in building something similar, I'd be more than excited to talk about it afterwards. So what is the point of testing in a proof assistant, right? I'm sure a lot of you have built systems that do things and you'd want to prove things about them or try to prove mathematical theorems. And at some point you found deep inside your proof that something was wrong and you couldn't actually prove false because, well, that's the point. So what QuickCheck enables you to do is find those bugs before, spot such bugs before you figure it out. So what do we have here? My basic example for the demo is here is a function that removes a natural number from a list of natural numbers. And if you were to inspect it more closely, you might already realize that it has a bug. But the point of this is, let's not inspect it more closely. Let's let a tool find it out. How do you find a bug in property-based testing? Well, you need a property. And the property in this case is this thing here, remove p, that says that if you give me a natural number and a list of natural numbers, then if I remove that number from the list, it should not exist inside that list afterwards. Fair enough. How does this work? Well, you can just process the command quick-check remove p. That's the thing that it adds to the language. And you'll see in your response buffer or whatever messages buffer your IDE has, that quick-check quickly comes up with a counterexample of the form 2 and the list 2, 2. So what happened here is that if you call remove with an element that occurs in the list twice, well, the then branch does not make a recursive call, so it's not going to remove it twice, the second time. So QuickCheck was able to find a bug by just generating random terms and finding a counterexample of the property and then minimizing it. That's what the shrink part over here is for. So how does this all work? Well, the first thing is that this had to be an executable property, whereas most things that we do in a proof assistant like Cog are inductive, and I'll talk about that later. But basically, there are 4 ingredients. There are 4 ingredients that we need in property-based testing. It's the property, like remove p that we had above. We need some way of showing counterexamples. We need some way of producing random inputs, and we need a way of minimizing counterexamples. And we're gonna demo the automatic way of doing that in Coq right now. I'm not gonna go into low-level details about how users can write these things themselves, although that's very much a possibility. So for printing, and for basically everything, QuickCheck uses type classes. This is very similar to Lean type classes. You have structures or records that allow you to define different operations on things and do ad hoc polymorphism. And for example, the show type class has one method that allows you to convert from some type to a string. It allows you to print things. And for example, let's see how that works. Let's define it ourselves first for just printing, and then see how it works automatically. So we have, for example, a type of colors, red, green, yellow, and blue. And after doing some Coq-specific things that are not really important, dealing with namespaces, you can just define an instance of print show for color. It takes a color, matches on it, and produces the appropriate string. Very straightforward, very mechanic, and afterwards you can just eval compute in it, which is similar to your eval in Lean. And then you get back green because it figures out that green is a color, and it figures out that a show type class exists and uses it to print it. Great. Now, writing these show instances is relatively straightforward, but it can obviously get very tedious. The more constructors you have, the more recursive things you have. When you want to start invoking other other show instances recursively, it gets tedious. So QuickCheck allows you to derive these things for free. So you derive show for color, and if you see what gets generated, it's basically the same instance with a bit more, with a few more details that have to deal with maybe allowing you to print things recursively at some point. But basically, you just get printing for free by deriving show. And if you want to have your own printer for some other reason, well, you can go ahead and do that. Same story with generators. The basic core of property-based testing is generating random inputs. And in QuickCheck, there is this type G of A, which stands for generators for some element of A. There is something called the monadic interface to it, which allows you to build these generators on your own if you wanted to. But for the common user of Cog, you don't have to dive into how generators work and how the underlying whole randomness is encoded and how you use seeds and do the plumbing to go from one generator to another. Instead, we can use type classes to hide that abstraction as well. What is that abstraction? That abstraction is called the gen and gen size type class. So there is a gen size type class, which again provides a single method, requires a single method, which is a function from a natural number to a generator of elements of type A. How does that work? Well, the natural number you can think of as a size. It's a fuel to bound the size of generated terms, and also coincidentally to ensure termination for the termination checker. So you can think of arbitrary size as a function that takes a fuel and produces elements of the type that you care about up to some size. Of course, writing such generators will be even more tedious than writing printers. So QuickCheck provides a way of doing that as well. So you can derive gen sized for a color. And when I say they become tedious, you're not supposed to really understand this without me explaining all the details, but you can see that there is some choice between the red, green, blue, and yellow colors being made. You choose one of them because that's what random generation does, plus a lot of other syntax and stuff. So that's the basic thing about shrinking and printing. All users need to write is derive gen sized and derive printing. So let's look at an actual example to see what happened. One of our favorite examples in functional programming is binary trees. So here we have the type of trees. They have leaves that are just leaves and nodes that take some kind of payload, a left subtree and a right subtree, just like you would write that in Lean as well. And then some Cog-specific stuff dealing with arguments that you can ignore. Now, QuickCheck users can just write this one line, derive gen sized and show for tree, and now they get access to a generator and a printer automatically. So you get some kind of printing, builds all the recursive stuff on its own, it's not important, and some generator. To showcase this generator and printing, let's have a property. We need a property. And the property that I'm going to introduce is something to do with mirroring trees. What do I mean by that? Well, imagine you have a mirror function that takes a tree and flips its left and right subtrees recursively. So a leaf remains unchanged, and node, the payload remains unchanged, but the right and left subtree are swapped and then recursively mirrored. So at the end of mirroring the whole tree, you'll have flipped it along a vertical axis, if you can think about that. And you also need some kind of structural equality on trees to define properties. So let's define it this way now. Simple recursive function. Leaves are equal, nodes are equal if every single one of the constructors things are equal. Although this can also be derived automatically in QuickCheck. So what's a property of mirroring a tree that we would like to test? Well, let's say that you want to test that if you mirror a tree twice, you get back the original tree. That is, mirror is unipotent. Fine. How do you test this assumption? You can simply use the for all property combinator here. And this receives some generator for elements of type A, and along with a property for things that operate on A's. So for all arbitrarily generated elements of the tree data type, mirror should hold, which takes a tree of natural numbers. And sure enough, if we let it run for a bit, like in 0.1 seconds, it ran 10,000 tests with trees up to size 5 and concluded that mirror P holds. And at this point, we gained some confidence in its truth, right? But what would happen if we had the wrong property here? Well, let's try to have a property that is faulty, which is that a tree is equal to its own mirror. And if you think about it for a bit, the smallest counterexample in this situation is not trivial. You have to have a node, and then one of those and the node has to have a subtree, and one of those subtrees has to be different than the other one in order to make this faulty mirror property fail. Not too hard to find, but not trivial. So QuickCheck will do some testing, and we'll come back with some counterexample that will go on and on and on. And here on the left, I have a different counterexample that was found earlier on when I was building the demo. And sure enough, like it found it very quickly in my tests, and after 4 tests here. But can you spot the bug right away? Yeah, like this counterexample has a ton of noise and it's way too big to be useful for a user. And that's where shrinking comes in. Shrinking is also known as delta debugging, and allows you to simplify counterexamples. How does that work? Well, there is an associated type class, and the type class is providing functions from an A to a list of A's that are somehow considered to be smaller. And the way this delta debugging algorithm works is, if you have found a counterexample, well, you call shrink on it, get a list of smaller counterexamples, and then try the property greedily on all elements of that list. If you find one that the property still fails on, well, that's a smaller counterexample, and you keep shrinking it in a best first search until you find a locally minimum counterexample. Okay. Of course, you can write these yourself, or you can derive them. And QuickCheck allows you to derive shrinkers. And if you see what they do, well, it's really hard to figure out what automatically generated code does. But here I have written something that is roughly equivalent. What it does is leaves cannot be shrunk. They're already minimal. While nodes can be shrunk to the left subtree, the right subtree, because those are smaller trees of the same type. Or you could try making something smaller, either the payload, the left subtree, or the right subtree, and then join all those results together. Eventually, if you keep doing this process, you'll get smaller and smaller trees and counterexamples. So sure enough, if we use a different combinator called forAllShrink, that takes the generator and the shrinker, we come back with one of the 2 minimal counterexamples. In this case, a node whose payload is 0, the left subtree is leaf, and the right subtree is node leaf. If you think about it for a bit, it's one of the 2 minimum counterexamples, and we get back that counterexample and can now debug our property or our system or whatever we wanted. Of course, this seems rather silly to have to write, right? Like, this is the generator that we have a type class for, this is the shrinker that we have a type class for. And in fact, QuickCheck automates that as well using type classes again. So QuickCheck users need only write something like QuickCheck faulty mirror P, and you get back exactly the same result. It picks some size, I don't think it's actually 5, internally, and progressively generates bigger and bigger counterexamples in order to test this property. And that's a QuickCheck in a tour de force. You derive generators, shrinkers, and printers. You have an executable property. You can just find counterexamples to it. If there are any questions, sorry, I didn't say that in the beginning, feel free to stop me and ask. Now, what about propositions? In a lot of, in Coq and in a lot of proof assistants, we have inductively defined things that we're trying to prove things about, which are, more importantly for this context, not executable. The answer that QuickCheck provides is again type classes. So we provide a type class that is decidable. So we have some kind of informative disjunction that says a property is either provable or not provable, and that is called the deck type class, which allows you a way of deciding with a witness whether a property is decidable. And we have another type class that encodes partial decidability, called deck opt. We probably need a better name for this, which provides one method that takes a natural number, a fuel that checks for whether a property holds up to some size, and returns an option bool. Why is that an option? Well, none means that there's not enough fuel to decide. Some true means, or some false means that it can conclusively decide whether the property holds. And we have these notations. You can write a question mark after a property in order to use a deck instance, and a double question mark with a fuel to use a checker. And obviously, the most common use of these things is in property-based testing. And in fact, the most common use is in testing equalities. And that's common enough that we have a specific type class, which is called decidable equality, which states that for all pairs of elements of a type, it's decidable whether x is equal to y. And for that, like we had for the tree above, QuickCheck defines a tactic that allows you to just derive that. So instead of writing EQ tree like we wrote above, we can just define an instance of equality for trees using one conveniently provided tactic. Armed with all of these things, we can now automatically test properties of trees that are written inductively. So above, we saw a faulty mirror property written as a function. Here, we write mirror t is equal to t, and this is a propositional equality, right? But using the question mark, we can just convert it, cast it to a Boolean check. We can check whether this property holds, and sure enough, faulty mirror p will find the exact same counterexample. Great. So that's the basic part of QuickCheck. But another very common occurrence in the kinds of reasoning we do in a cockproof assistant and in many proof assistants is that properties have preconditions. For example, you might be dealing with balanced trees or red-black trees or AVL trees or any other kind of precondition. And in that case, it's a very common occurrence to have properties that have such inductive definitions as conditions before the conclusion of the theorem. Here is a definition of what it means for a tree to be balanced. Again, this is the syntax in Coq. You have a relation that is an inductive type that is parameterized, indexed by a natural number in a tree. We have three constructors. Leaves are balanced at both 0 and 1 because you are allowed to differ in heights by 1. And nodes are balanced at height n plus 1 if its left and right subtrees are balanced at height n. And whenever you would implement a self-balancing data structure or anything like that, you would have some kind of property like balanced. So let's implement a naive insertion function and figure out what happens when things go wrong. So here it is. We insert, if we find a leaf, we just insert the element there. And if we find YLR, we just insert it at the leftmost subtree. So we just keep recursing and insert something at the leftmost point of a tree. Obviously, this doesn't preserve balance, right? If you keep inserting things on the leftmost thing, at some point, you're going to, at some point very quickly, we're going to run into something that is not balanced. But to check if a tree is balanced, we need a computable way of deciding whether balance holds. And QuickCheck actually does that. You have a way of deriving a partial decision procedure for inductive relations. And this gives you a checker, an instance of the decked opt type class that you can actually run. And it's basically something that says that for all natural numbers and all trees that you give me, then I will give you a way of testing it, potentially with some fuel. And now we can use this to check whether something is balanced. So for example, we can check if node 4242 is balanced. Node 42 leaf is balanced at height 1, which it is. We can check if a leaf is balanced at height 2, which it isn't. And we can try to check something that we don't provide enough fuel to check, and it will come back with none. So you can basically run inductive relations. This is probably not the most efficient partial decision procedure, but it's there. And now we can use that in a property. So let's try our first obviously false property just to see how that works. This says that all trees are balanced. If you give me an arbitrary natural number and an arbitrary tree, this will check whether the tree is balanced at that height. Obviously wrong. How do we get that? Well, the first thing that will happen is that eventually we'll get a node and number 0. That's obviously false. But we can also derive generators for satisfying these kinds of preconditions. So for example, we can derive a generator that produces trees that are balanced at a given height. So this produces an instance of a different type class that allows you to use constraint generators. And that constraint generator that we get says that for all natural numbers, I can generate trees such that balanced n tree holds. The definition itself gives you access to one method, like gen sized before, that gave us arbitrary size. This one gives us arbitrary size such that, st, which has the same signature. And the only difference is that it produces a maybe element of the type, because obviously we can't generate for every single inductive type. Now, armed with these, we can just, of course, first sample balanced trees, which are always balanced at height 1. You'll get some leaves, some nodes. And now we can write properties. And this is the part that is not fully automated yet, but we're working on it. Basically, in order to check a property that would require you to use one of these complicated constraint generators, you have to write it yourself, using for all and for all maybe combinators. So you can say, I will generate an arbitrary number by choosing a number between 0 and 5. You can generate a tree such that it's balanced at that height. And then I'm going to test that all of these trees generated are balanced at that height. And sure enough, if I do that, it will pass 10,000 tests. Great. Now, let's go back to the original property that I mentioned we want to write, which is that insertion preserves balanced, which it shouldn't, because we wrote a thing that inserts it on the leftmost thing. If we just try to use naive quick check that generates random numbers and trees and try to generate to see if it presents this balance, well, after a bit more time, we'll figure out that, well, it could not generate a single tree that is balanced at height 5 or whatever I picked here, because it's basically impossible to generate a balanced tree by accident. However, if you write your own property, which states that, oh, I'll only generate trees of height n for the height I want, and then choose an arbitrary integer x to insert, well, I can very quickly find a counterexample after just 6 tests. And I haven't implemented a shrinker here because that would be a bit more complicated, but you can use the shrinker from before and do some kind of filtering. Yeah, and that brings me up to 25 minutes. That's basically what I have. You can, for generic properties without preconditions, in Coq, you can now derive printing generation and shrinking and get a tester for free. If you have an inductively defined theorem, like insertion preserves balance here, a theorem that is specified using inductively defined conditions and properties, then you have to write the property itself. You have to figure out what you want to generate and how, but you can automatically test things. And there is a question. Yes?
Yeah, thanks for your talk. I've got two little questions. So first, you've got this common quick check that you're running, but is it possible to just run the thing in the middle of the proof when you're proving something and use the current goal as the assertion you want to test and the current assumptions as a as the such that clause or something like this?
Yes, that's a great question. And that was recently added again as a feature. It was broken for a long time because COG is a research artifact and it's still being maintained and things break. We added it back in, but it's using this tag, the thing that is the most naive version. Actively trying to test the current goal is something we're researching right now, because it's not clear, for example, when you have multiple inputs and multiple conditions, what you have to generate and in what order, right? That's a hard problem. So once we figure that out, you can do it in an arbitrary goal. But yes, you should be able to use it at some point in the near future that way.
And what about testing properties of statements involving many type classes? I don't know if you want to find a group that is a counterexample to your current statement, and also you need to have a data and satisfying a bunch of type classes. Is there anything like
that can happen in general, like depending on what do you mean by satisfying. One of the things I was looking in coming here and giving this talk was, for COC, I know the kinds of proofs that we do, I know the kinds of properties that we're trying to prove, and the user I have in mind for QuickCheck is me. So I know what we're using, I know what we want to generate. For Lean, I don't have that, right? So if there is a kind of constraint that you would want to generate, and you would want to be able to do the same thing automatically, then I'd love to talk about it. But yes, in general, there are a couple of papers on how you can generate data satisfying arbitrary constraints, in a particular fashion, and then do the same thing.
All right. I think David had a question next.
Thanks. Thanks for the talk and the demo. Do you have a ready example of the mutants feature in QuickCheck? Because that sounds like a really useful thing to have.
The mutants feature. I'm not sure I have a demo that currently works now because this is a demo build that I have because I haven't using one fancy feature. Sure. But I can show you what it roughly looks like. So if you see the mutation testing tutorial, wait, that's a very stupid one. Benchmarks STLC. That would not have it. Did that have it? Nope.
Maybe we should take a look at this some other time.
Take a look at it some other time, but basically it allows you to have things like this. This is a very stupid bug, that's why I didn't want to show this. But basically you can add mutants, which is, I'm assuming you meant that by mutation testing. There are two kinds of things you might have meant. You can add mutants, which are, okay, this is the correct implementation of +1. This is a buggy implementation of +1. This is another buggy implementation of +1. And you can use this along with the command line, sadly, tool that allows you to make sure that your generators can find all of these bugs.
Thank you.
Yep. And
I guess one more question from Joachim, and then we'll close.
Hi Leo, good to see you again. I have a question direct in like the UX corner in a way. It's very useful to run QuickCheck or something like this when you suspect that the theorem isn't correct, but it's even much more useful if it's running on those theorems where you don't expect them to be incorrect and you're being told they're incorrect. Yep. I believe the Isabel people have actually their nitpick variant of this running automatically to be right a lemma. Is this something you can do in COG, and what will the users report about that? Or is it something
it's something we have been working towards in the last 10 years almost, right? Like every single thing you see here that is automatically derived is basically a different research paper. So at this point, we can derive everything except for the final property. Once we can do this as well, once this is able to be derived automatically, then there's nothing really stopping us from forking a process in the background and doing that whenever you write proof, for example, or some other keyword that allows you to do that. So I think that will come in the moment we have the tooling support to do that. But yes, that's definitely something we want.
Okay, looking forward to that.
Wonderful. Let's thank Leonidas.